Thermodynamics is often introduced as the study of heat and temperature, but that definition is too narrow to capture its real power. At its core, thermodynamics is the science of energy transformation under constraints. It asks not only how much energy exists, but how energy moves, in what form, and with what unavoidable losses. That is why it applies to engines, refrigerators, chemical reactors, weather systems, and biological metabolism. The subject works with macroscopic variables such as pressure, volume, and temperature, which means we can analyze entire systems without tracking every molecule individually. This macroscopic viewpoint is practical and profound. It gives rules that hold across enormous complexity. A combustion engine and a living cell are very different mechanically, yet both obey the same thermodynamic limits. In this sense, thermodynamics is less a specialized topic and more a general operating system for physical reality. Before the laws, we need clean definitions, because confusion usually starts with language. Energy is a state property. A system can possess internal energy. Heat and work, by contrast, are modes of transfer across a system boundary. Heat is energy transfer driven by temperature difference. Work is energy transfer through organized forces acting over displacement, such as a piston being pushed. This distinction is not a technicality, it is central to correct reasoning. A hot object does not contain heat as a stored substance. It contains internal energy, and heat is what we call that energy while it is being transferred due to temperature differences. Once boundary thinking is clear, thermodynamics becomes a disciplined accounting method. We define a system, define surroundings, then track what crosses the boundary and how state variables change. This framework prevents vague explanations and makes different physical processes comparable through the same conceptual structure. The historical origin of thermodynamics shows why it became so rigorous. It did not begin as abstract philosophy. It began as an urgent engineering problem during the steam age: how to make heat engines more efficient. In 1824, Sadi Carnot analyzed idealized heat engines and introduced the Carnot cycle, a conceptual benchmark for maximum possible efficiency between two temperature reservoirs. Carnot's work reframed engineering from trial-and-error improvements to fundamental limits. Instead of only asking how to build a better machine, he asked what no machine can ever surpass. That shift changed science and engineering permanently. It implied that performance has universal ceilings rooted in nature itself. Later researchers corrected and expanded Carnot's interpretation, but his core insight survived: temperature differences define opportunity, and some efficiency losses are unavoidable. Thermodynamics therefore grew from practical machinery into a law-based theory that distinguishes what is improvable from what is fundamentally impossible. As the field matured, Kelvin and Clausius helped transform scattered insights into formal principles. Kelvin contributed early definitions linking heat and mechanical effects, pushing the discipline toward measurable consistency. Clausius, building on Carnot, articulated key forms of the second law and introduced the term entropy in 1865, giving science a new quantity for tracking directional change in energy transformations. This was revolutionary because the first law of energy conservation alone could not explain why certain processes occur naturally and their reverse does not. Clausius also strengthened thermodynamic reasoning by clarifying cyclic processes and irreversibility. Around this period, thermodynamics became less an engineering craft and more a general physical framework. It gained a clear vocabulary, sharper mathematical structure, and broader scope. What started with steam engines now had the conceptual tools to address chemical reactions, phase changes, and eventually links to microscopic physics through probability and large number behavior. The zeroth and first laws established thermodynamics as a coherent measurement and accounting system. The zeroth law states that if system A is in thermal equilibrium with B, and B with C, then A is in thermal equilibrium with C. This transitive property sounds obvious, but it is the logical basis for temperature as a meaningful scalar quantity and for thermometers as universal instruments. Without it, temperature comparisons would not be reliable across systems. The first law then formalizes energy conservation. The change in a system's internal energy equals heat added to the system minus work done by the system. This law guarantees bookkeeping consistency. Energy cannot be created from nothing or destroyed into nothing within ordinary thermodynamic processes. But it can redistribute among forms, and that redistribution matters. A process can conserve total energy and still be useless for practical work. So the first law is necessary, but by itself it does not tell us which transformations are feasible in real time. The second law is where thermodynamics acquires direction and practical bite. It states, in one common form, that total entropy of an isolated system does not decrease. This introduces an arrow to physical processes. Heat flows spontaneously from hot to cold, not the other way around without external work. Friction converts organized mechanical motion into dispersed thermal energy. Mixing occurs naturally, unmixing requires intervention. Entropy is often loosely described as disorder, but for deeper intuition it is better seen as the spreading of energy into more numerous microscopic configurations, reducing concentrated availability for work. This is why no heat engine can be 100% efficient in a cycle. Some absorbed heat must be rejected to a colder sink. The second law therefore sets absolute limits on engines, power plants, and conversion technologies. It also explains everyday irreversibility. Smashed glass does not spontaneously reassemble, not because energy is missing, but because statistically and thermodynamically, reverse trajectories are overwhelmingly improbable. The third law addresses low-temperature behavior and the approach to absolute zero. In essence, as temperature approaches 0 Kelvin, entropy approaches a minimum value for a perfect crystal, and absolute zero itself cannot be reached by any finite sequence of thermodynamic operations. The practical implication is that cooling becomes progressively more difficult at extreme low temperatures. Each additional reduction demands disproportionately more effort and increasingly refined techniques. This law is not merely philosophical, it affects cryogenics, superconductivity experiments, quantum technologies, and precision metrology. Together, the laws form a layered architecture. The zeroth defines temperature consistency. The first conserves energy, the second constrains direction and efficiency, and the third governs the limiting behavior near zero temperature. Understanding them as an integrated system is more useful than memorizing isolated statements. Any proposed device or process must satisfy all these constraints simultaneously, which is why thermodynamics remains one of the strongest filters for distinguishing realistic innovation from impossible claims. Thermodynamics quickly expanded from mechanical engines to chemistry, where it became indispensable. Chemical thermodynamics studies energy and entropy changes in reactions and phase transitions, helping determine whether a process is energetically favorable under given conditions. This is where concepts like free energy become crucial, because they combine enthalpic and entropic effects into criteria for spontaneity at constant temperature and pressure. A reaction releasing heat is not automatically sufficient for useful conversion. Entropy and environmental constraints also matter. Conversely, some processes that seem unfavorable can proceed when coupled to others, especially in biological systems where metabolic pathways chain reactions strategically. In industry, chemical thermodynamics guides reactor design, separation processes, battery chemistry, and materials synthesis by mapping what states are achievable and where equilibrium lies. It does not directly provide reaction speed, which belongs to kinetics, but it tells whether a target state is thermodynamically accessible at all. That distinction prevents costly confusion between possibility and pace. A common question is how macroscopic laws emerge from microscopic particles. Statistical mechanics provides that bridge. Matter contains vast numbers of atoms and molecules, each moving and interacting according to underlying physical laws. Tracking each particle is impossible, but statistical treatment of ensembles reveals stable aggregate behavior. Temperature corresponds to average microscopic kinetic behavior, pressure arises from momentum transfer at boundaries, and entropy relates to the number of microscopic arrangements compatible with a macroscopic state. This perspective strengthens the second law. High entropy macrostates dominate because they can be realized by vastly more microstates. So systems evolve toward those states not by mystical preference, but by overwhelming combinatorial likelihood. Statistical mechanics therefore explains why thermodynamic regularities are so robust despite microscopic complexity. It converts thermodynamics from a purely phenomenological discipline into one grounded in particle-level reasoning, while preserving the practical power of macroscopic equations engineers use every day. Beyond empirical and statistical development, thermodynamics also gained formal mathematical depth. Konstantin Karatheodori and others presented axiomatic approaches showing that thermodynamic relationships can be built from rigorous postulates, not only from historical engineering intuition. This mathematical refinement clarified distinctions between state functions and path-dependent quantities, between reversible idealizations and irreversible real processes, and between local differential relations and global process constraints. In practical terms, these refinements improve conceptual discipline. They prevent misuse of formulas outside valid conditions and help experts navigate complex systems where multiple constraints interact. The value is not just elegance. Strong formal structure increases reliability across disciplines, making thermodynamics portable from mechanical engineering to geophysics and from electrochemistry to atmospheric science. A mature theory is one that survives translation, and thermodynamics does because its principles are both experimentally anchored and mathematically coherent. That combination is rare, and it explains the field's enduring centrality. In modern life, thermodynamics shapes technologies and policy questions even when people do not notice it directly. Power plants are constrained by cycle efficiencies and heat rejection requirements. Refrigerators and heat pumps, now critical for building decarbonization, operate by moving heat against natural gradients using work, a direct application of second-law principles. Electronics depend on thermal management. Without efficient heat dissipation, performance and reliability collapse. Meteorology and climate science rely on radiation balance, latent heat, and large-scale energy transport. Biological systems maintain local order by exporting entropy, illustrating compatibility between life and the second law. In each case, thermodynamics does not eliminate innovation. It channels innovation toward strategies that respect reality, reducing irreversibility, optimizing temperature differences, improving coupling, and minimizing waste pathways. Engineers who ignore thermodynamics chase impossible efficiencies. Engineers who understand it find real leverage. The field is therefore not only descriptive science but strategic guidance for building workable systems. The strongest takeaway is that thermodynamics teaches disciplined realism. It tells us energy must be accounted for, but also that not all energy is equally useful for doing work. It tells us change has direction, efficiency has ceilings, and extreme states have asymptotic barriers. Historically, it emerged from steam engines, but it now governs chemistry, industry, atmospheric dynamics, and advanced materials. Conceptually, it links measurable macroscopic behavior to microscopic statistics and rigorous mathematical structure. Practically, it helps us evaluate claims, design better machines, and avoid impossible goals. If you keep one mental model, keep this: every real process is a negotiation among conservation, directionality, and constraints. Thermodynamics is the rulebook for that negotiation. Once you see the world through that lens, complex phenomena become less mysterious. You start recognizing why some transformations happen spontaneously, why others demand external work, and why every useful system operates within limits that cannot be engineered away. If you found this helpful, please like this video and subscribe for more explainers.